Okay, let's continue our discussion on the section 16.e for the Pareto optimality and its relationship with social welfare optima. Okay, so previously we defined two different sets. The first one is called utility possibility set, capital U, and based on that, we defined the Pareto frontier UP, which is sort of essentially a restatement of the Pareto optimum, right? Okay, so let's continue our discussion and to give this proposition 16.e.1, which establishes the connection between a feasible allocation and the Pareto efficiency. Okay, and see what's the condition of that. Okay, so we say that a feasible allocation xy, which is a tuple including all the x's from x1 to xi, from y1 to yj, so that is Pareto optimum. Okay, Pareto optimum if and only if, so we're going to have both two directions. If and only if the utilities from U1 up to UI, so this tuple, that will be an element of this UP. Okay, so this is the statement of this proposition. So we're going to try to prove this. So we're going to prove by for both two directions, we're going to prove both of those by the contrapositions. Okay, so the first direction, we're going to assume that, let's say if those utilities, they are not an element of UP. So you can refer to the definition that we gave from the previous episode. And there's going to be, because we do not have this as element, so there will be, or there is some utilities or U1 prime up to UI prime. So this is in the set of U, okay? And such that we have those UI prime to be greater than or equal to UI xi for some I, and to be strictly greater than of those for some i's. Okay. But the problem is that now this U1 prime up to UI prime, so this is in U only if there is a feasible allocation, okay, x prime y prime, such that UI xi prime is greater than or equal to UI prime for all I. Right? And then it immediately follows that x prime y prime will Pareto dominates the xy, right? Okay, good. So that would be this direction, right? Good. Now let's suppose, okay, for the other direction, if xy, it is not a Pareto optimum, then it will be Pareto dominated by some feasible allocation x prime y prime. Okay, we shouldn't use x prime y prime, but okay, this is not the same as one before. Okay, by some feasible x prime y prime, which means that ui xi prime greater than or equal to ui xi for all I, and ui xi prime strictly greater than to ui xi for some I, right? Okay, therefore u1 x1 up to ui xi, this is not in UP, and then this finishes the second contraposition. Okay, therefore we say that a feasible allocation is a Pareto optimum if only if all those corresponding utilities that would be together, that would be an element in this UP. Okay. All right. So that would be the relationship between those two things. Okay, so next, we're gonna also introduce the social welfare function. Okay, that we mentioned in the beginning of this episode. Okay, or this section. Okay, so now suppose that the society's distributional principles, it can be summarized by some social welfare function. Okay, so that'll be okay. So suppose the society's distributional principles or mechanisms, okay, more precisely, can be summarized in a social welfare function. Okay, which is denoted by this capital W. Okay, so that's another notation. So don't mix up this W with wealth or omegas. Okay, U1 up to UI, and that is assigning social utility values to the various possible vectors of utilities for the I consumers. To basically all possible vectors of utilities for all the consumers. Okay. All right, and then we're gonna concentrate here and follow the textbook to concentrate on particularly simple class of the social welfare functions where it has a linear form. So W, U1 up to UI, that'll be simply the summation over I with some parameter lambda I and UI. So this lambda will be just sort of some weights for different consumers. Okay. All right. So, and where we have this, so this lambda will be just a vector, okay, from 1 up to y. Okay. All right. And if we want to let this u to be also vector, then this wu can be written as lambda u. Okay. And because social welfare should be non-decreasing in the consumer utility levels, and we assume that the lambdas are greater than or equal to 0. Okay. And then with this, okay, we're gonna have a problem where we can to study some problem where we can select the points in the utility possibility set U that can maximize our measure of the social welfare, right? So essentially, we can solve this problem, maximizing by choosing the U in the capital U. So all those possible U's, where we're gonna maximize our social welfare. Okay. So that'll be maximizing a linear social welfare function. Okay. So, and intuitively, for example, in the figure where we have this U1 and the U2, okay, for example, if we, as before, we have this set of U below this curve, okay, so essentially we're just, again, just moving, shifting a straight line, right, and try to find that solution. So that'll be just some tangent line to this boundary. Okay, and that gives us this solution U star. Okay, and that lambda that'll be some vector which is tangent or which is orthogonal to this tangent line, right? Okay, good. So that'll be just an illustration of this mathematical problem. So next, we're gonna use a proposition to establish the result that we have for this problem. Okay, and that's gonna be 16.E.2. Okay, so we say that if U star, okay, as the solution to the problem from U1 up to UI star is a solution to the above problem. Okay, with lambda be positive vector. Then we're gonna say that U star is in UP. Okay, so that is saying U star is the utility vector of a Pareto optimal allocation. Okay, so that's the definition for this UP. Okay, so that's one direction. Moreover, if the set, so if the utility possibility set U is convex, then for any U tilde, okay, from U1 tilde up to UI tilde, so for this vector in UP, there is such lambda, right? There is a vector of welfare. So this is just saying the other direction, okay? Lambda, which is from lambda 1 up to lambda I, okay? Where this lambda is not 0. And such that we have lambda inner product U tilde greater than or equal to lambda inner product U for all U. Okay, so that means this U tilde is a solution, okay, to the problem. Okay, good. So let's prove this. Okay. So the first part will be pretty straightforward. Okay, so we're gonna say that if U star is or were not, or is not Pareto optimal. Okay, I'm gonna use the contradiction again. Then there exists some U where this U greater than or equal to the U star, this than the original solution, and then because we have this lambda greater than 0, we have lambda U strictly greater than lambda U star, okay, and that'd be the contradiction. Okay, so for the second part, okay, it's a little bit complicated, okay, and we're gonna use the supporting hyperplane theorem, and we notice that if U tilde is an element of UP, then U tilde is in the boundary of the U, okay? So you can refer to the section endpoint G in the textbook and which is talking about all those mathematical appendix, and by supporting hyperplane theorem, okay, so there exists a non-negative non-zero lambda such that lambda inner product u tilde greater than or equal to lambda inner product u for all u in the capital U. Okay, and that's not finished yet. So moreover, since the set U has been constructed so that we're going to have U minus R plus I, that is a subset of U. Okay, so essentially means that we can have some waste, right? Free disposal. We must have lambda to be greater than or equal to 0. Okay. Okay. In other words, or specifically, if lambda I less than 0, then we can choose a U in capital U with ui less than 0, okay, large enough in absolute value so that we would have lambda u greater than lambda u tilde. Okay.